Uh, Good evening, everyone. So, let us begin today's session. So, in this week, Sir has covered thrust loading, power loading, wing loading, and conversion of thrust loading and wing loading from different arbitrary flight conditions to the takeoff condition. And then he has covered the estimation of uh, thrust loading from different phases of flight and estimation of the wing loading from different phases of flight. So first we'll discuss that what is thrust loading, power loading and wing loading. So the thrust loading is defined as thrust by weight. So how much percentage of the weight can the aircraft give as the thrust? So obviously you can guess that uh, like generally when we fly aircraft, like if it is a commercial aircraft, it will have a low kind of thrust loading. It will have T by W less than 1. The more thrust the aircraft has, the more uh, the force it has. So the more aerobatic things it can do. Like a normal aircraft which is flying straight, it cannot uh, climb vertically up. Okay, but a fighter aircraft which has a T by W more than 1, it can also climb vertically up. Okay, so a aircraft with a higher thrust loading, it will climb faster, it can go faster, max velocity will be higher, rate of climb will be higher, all these things that is. But the disadvantage is that the higher thrust may require a bigger engine, which will increase the weight, and also the fuel consumption might be high. Then we have the power loading. So power loading, it is so conventionally power loading is defined as weight by horsepower. So the thrust loading is mainly meant for jet engines and jet aircraft, and the power loading is meant for propeller driven aircraft. Now conventionally for jet engines the thrust loading is defined as T by W, whereas for propeller aircraft it is defined as weight by horsepower. So you can see that in a way this is opposite of the thrust loading. So if thrust loading is T by W, the power loading should be P by W, but it is due to convention or due to historical trend, it is defined as weight by horsepower. Then we have wing loading, which is W by S. So in a way, this defines how big the wingspan of the aircraft is. So if this is the top view of the aircraft, then how big are the wings? Like for a glider, it has a low wing loading because the wings are very large. The wingspan is large. Whereas, but a large wingspan, it although it has some advantages like it reduces the induced drag, but a larger wingspan makes the aircraft sluggish to control. So it will take more time to make turns and maneuvers. So you will also see that fighter aircraft have smaller wings. Okay, so the wingspan is smaller, so the wing loading is higher. So the requirements of thrust loading, power loading, wing loading, these are also dependent on the applications of the aircraft, like what kind of application the aircraft is going to do. So so this point is there. Note that power loading is inversely defined compared to thrust loading, and so for propeller aircraft we talk about power loading, but if we can also convert it back into a thrust loading for comparison, like if we want to compare uh, a jet engine with a power engine with a propeller engine, or like a jet aircraft with a propeller driven aircraft, then we can use such kind of a formula to convert this power loading into thrust loading. So what you do is you have to multiply it with 550 into eta p. Eta p is the propeller efficiency, and v is the velocity. So the velocity you are considering. You know that the power is dependent on the velocity of flight. Power is equal to thrust into velocity. So the thrust loading, it will change with the, for a propeller aircraft, the equivalent thrust loading, it will change with the flight velocity, and then you divide it by hp by weight, which is inverse of the power loading. So the equivalent thrust loading is 550 eta p v into 1 by power loading. Okay, now moving on. So these are some like representative T by W and horsepower to weight ratios for different types kinds of aircraft. So for jet, so the upper one is for jet aircraft and the bottom one is for propeller aircraft. So for jet trainer, you can see that T by W is 0.4. For jet fighter, which is dog fighter, T by W is 0.9. Other kinds of fighter are 0.6, and military cargo and jet transport, they have T by W of 0.25. So now you can see that aircraft which require more, aircraft which require faster turns, okay, or more aggressive turns, they have higher T by W, whereas aircraft which are transport aircraft or cargo aircraft, they have a lower T by W. So this is because, as I said, a higher T by W allows you to um, make more aggressive maneuvers. Then for propeller aircraft, okay, so here there are two columns. First one is HP by W, so horsepower by weight, and then the inverse of that is also given in the other column, which is weight by horsepower, and this column is defined as power loading. So you can see powered sail plane is 0.04, and home built aircraft is 0.08. General aviation is 0.07 for single engine. For twin engine it is 0.17. Agricultural it is 0.09. Twin turboprop it is zero point 0.2, and for flying boat it is zero point 0.1. Now since the power loading is uh, inverse of HP by W, so a lower power loading implies a more like powerful aircraft. So out of these, obviously the twin turboprop, it has a higher horsepower to weight ratio, so you can see it has a lower power loading. So for a jet aircraft we have a higher, and for propeller aircraft it is lower. Okay, now moving on. So the other thing is conversion of all these ratios to the takeoff condition. Now typically what is done is that your flight has several stages, such as this takeoff roll, and then we have the climb phase, and then the cruise phase, loiter, and landing. Now for each of these phases of flight we have different uh, thrust to weight, and uh, for different phases of flight we have the thrust loading and wing loading requirements, but we have to convert all of this back to takeoff condition for comparison. Okay, like let us say over here we require, like for takeoff we require, let us say T by W of 0.1. No, let us say for takeoff we require T by W of point 0.8. For cruise we require 0.1. For climbing we require 0.5, and for loitering we require 0.2, and landing also we require 0.1. So let us say these are the ratios. Now obviously out of these the maximum one is 0.8. So we have to select our engine in such a way that it gives this 0.8 thrust to weight ratio during takeoff. Okay, now when we are choosing the maximum of all of these have to be the same kind of quantity to come for proper comparison, right? So these quantities they have to be converted back into the takeoff condition. So the issue is that when the aircraft is flying, the weight of the aircraft will go down, and also since the aircraft is going into higher altitudes and then again coming down to lower altitudes, the thrust produced by the engine will change, and this approximately varies with rho at the altitude by rho at sea level into the sea level thrust. So approximately by this relation the thrust will vary. So the thrust to weight ratio at this phase, at the cruise phase, you have to convert those values back. Okay, so let us say that your T by W at cruise phase is 0.1. So then 0.1 is approximately equal to rho air density at that altitude by air density at sea level into thrust at sea level. So from this you have to find that what will be the thrust required at sea level. Okay, and similarly we know that uh, during the takeoff and the climb phase some of the weight will be lost as fuel burned. So you have to find out that if the weight over here is something, then what will be the corresponding takeoff weight, and using that you have to then convert. So for jet aircraft you have to use this formula to convert. Uh, in this example we are converting cruise thrust loading to takeoff thrust loading, and for propeller aircraft you have to use this formula. So you can see it's simple. This is the cruise thrust loading, and over here we are multiplying it with the weight at cruise by weight at takeoff. So in the second week we saw that how this conversion can be done, like how can we estimate the cruise weight and the takeoff weight. So how to find this ratio, we have seen it in the second week. So using that we can find this, and the thrust at takeoff by thrust at cruise we can find this from the engine manufacturer's chart, or we can use this approximate relation and find that out. Similarly for propeller aircraft, uh, the relationship is actually the same. Here in place of L by D you can also write thrust by weight, because instead of this parameter you can also write thrust by weight, because you know that in cruise lift is equal to weight and drag is equal to thrust. So you can replace those values, it will come out to the same kind of formula. Okay, now moving forward. So these are some figures that I've taken from Raymer's book. So these figures, they depict the thrust, how the thrust and the power changes with altitude. So the first one is for jet engines. So this is T thrust at the altitude by the takeoff thrust. So you can see it is a fraction 0 0.1, 0 0.2, 0 0.3 up to 0.7, and in the y-axis we have the altitude. So you can see that with altitude the thrust it decreases for both kinds of engines. And similarly, you can the second figure is for propeller aircraft. Uh, you can see that the how the horsepower of the aircraft it decreases with altitude. Okay, now I am going to talk about some simple ways how we can estimate the thrust loading and the wing loading from different phases of flight. So we have to consider a simple aircraft mission requirement which consists of takeoff and climb, cruise, loiter, and landing. So for each of these phases, we will use the fundamental equations to get the value of T by W and W by S. So first, when we consider the takeoff phase, we know that the aircraft has to accelerate up to some kind of some takeoff velocity. So we know that usually the takeoff velocity is about 1.3 times the stall velocity. And the stall velocity is given by 2 into W by S by rho into CL max. So if the aircraft is like this on the ground, so you have to then consider then what are the forces acting on the aircraft. So first we have the thrust which acts in the forward direction. Then you have the drag force, and you also have the friction from the wheels. Okay, and I'm ignoring the forces in the y direction. So therefore the equation of motion will be ma equal to t minus d minus f. Okay, so from here then you can divide it by the weight of the aircraft. So weight is mg. So then what you can do is in the left hand side you can multiply and divide by g, and this is the weight. So you can divide it by the weight and you can rearrange it to get this equation. Okay, now obviously over here the drag will be drag is variable and the friction force is also variable, because you know that the friction force is equal to friction coefficient into the weight. Okay, now the friction, okay, the friction force is equal to mu into n, the normal force, and in this case the normal force is equal to uh, weight minus lift. So both the friction force and the drag force they vary as the aircraft is accelerating. Okay, so this is not as simple as it is written in the equation, but as a first approximation you can consider it like this. Okay, now and for the acceleration, so how much acceleration will you need to perform the takeoff? That also you can estimate it from this equation. Okay, and over here the initial velocity is 0, so the acceleration is equal to v square by 2s. So the final velocity is the takeoff velocity, and s is the runway length. So if you know the runway length, or if you know that in how much distance the aircraft has to take off, you can calculate the required acceleration, and from the required acceleration you can then calculate the thrust loading. Now let me erase this. So I am trying to show that how you can use these equations to calculate the thrust loading and wing loading at different phases of flight. Then for the climb phase also we can write the fundamental equations. If we consider that the aircraft is climbing at this climb angle of gamma, then we can draw the free body diagram. And now you can resolve the components. So if I only consider the thrust axis, then okay, so this is the equation along the thrust axis. Now if I consider that the aircraft is in a stable climb, so not accelerating, then the right hand side is 0, and then we can rearrange the equation and we can divide by the weight to get. Now in this equation we can consider that the lift is approximately equal to the weight. So this is not really true, because you can see that the lift and weight, they do not exactly balance each other. But if gamma is small, then this equation is approximation is valid. So if we consider this, then we can write thrust by weight equal to sine gamma plus 1 by L by D. Okay, so the L by D is usually on the order of 10. L by D is usually on the order of 10. So this part of the equation is of the order of 0.1. Okay, so the contribution of this fraction is only 0.1. So the major contribution is comes from the sine gamma term. So in climb, the thrust loading required, it mainly depends on the climb angle. If you have a higher climb angle, then it will require a higher thrust. Now you can perform the similar kind of thing for cruise and for maneuvers. So now you can draw the aircraft diagram for a cruise flight. So you know that thrust is equal to drag and lift is equal to weight. So if you divide T by W, you can also divide it by drag by lift, which comes out to 1 by L by T. So the as I said previously that the lift to drag ratio is on the order of 10. So the thrust loading at cruise, it is on the order of zero point 0.1. So actually in cruise condition very little thrust is required to maintain the cruise velocity. Finally, if you consider the maneuvers, during maneuvers, you know that the lift is proportional to lift is equal to N into weight. Okay, so since the lift is equal to N into weight, if you plug it into the equations, you can get that for maneuvers, the thrust loading is N by L by D. So it is quite intuitive also how the during maneuvers, since you require N times the force, the thrust loading is also N times. So here I have again written the takeoff distance. How do you calculate the takeoff distance, or how do you calculate um, the takeoff acceleration, and also the vstall. So as you remember from the vstall equation, is this. So if you know the vstall, like let us say that the vstall requirement is given somewhere, or there is some specification which is mandated by aviation authorities, then you can invert this equation to find the wing loading also. So you know that the so if you invert this equation, you can get half rho v. Hmm. So the wing loading can also be found from this equation if you know the vstall. And as you know that v takeoff, it is approximately equal to 1.2 to 1.3 times vstall. So if we are considering the aircraft which is performing the takeoff role, then these are the forces acting on the aircraft. And then using Newton's equation, we can write it as like this. Okay, so the thrust requirement during takeoff, it is this. Now, as the aircraft is accelerating on the runway, the drag will increase and the frictional force will decrease. So the quantities, so the second and third term in this equation, they are variable. Okay, but as a first approximation, we can consider that the thrust requirement is equal to acceleration by g. So with how many g's of acceleration, like how many g's of acceleration do you need? And we can also find out this acceleration if we know the takeoff distance. So we know the formula v square minus e square is equal to 2as. So over here I have also considered that the acceleration is constant. This will not be the case if since the thrust, drag and the force, friction force all are varying, so the acceleration is not constant. But as a first approximation we can consider constant acceleration. So over here the final velocity is the takeoff velocity and the initial velocity is 0. So we can find the acceleration using the near s is the takeoff distance. So then we can write it as a equal to, so if the takeoff distance is provided by some specification, then we can find the acceleration, and then using the acceleration we can find the thrust requirement. Now I'm going to talk about wing loading. So wing loading also you have to find it out from the fundamental equations of the each of the phases of flight. So as you saw that for takeoff, if the stall velocity is given, then you can find out the wing loading using this formula. Similarly, for the cruise phase, like you know that for cruise phase, if you are for if you want to maximize range or if you want to maximize the endurance, you have to fly at a specific CL. So for like to maximize range, you have to fly it at no sorry to minimize the thrust requirement. So minimum thrust. So for minimum thrust, you have to fly it at CL equal to root over CD naught by K. So then you can use this CL to find out what will be the uh, wing loading. So then K is equal to 1 by pi into aspect ratio into E. So the CL is equal to CD naught pi AR into E. Now you can write that so in cruise we can write that lift, which is also equal to the weight, this is equal to half rho v square s cl, and this half rho v square which is it is called the dynamic pressure, also represented by q. So we can write w equal to q s cl, and cl you can replace by this quantity, and you can divide by s to get the wing loading. Now similarly for the jet aircraft, if we want to maximize the range, we'll have to fly at CL equal to CD naught by, I think, by 3k. Hmm, by 3k. So then if you again follow this procedure, you will find that the wing loading is this: q square root of pi aspect ratio E CD naught by 3. And similarly for maximum jet loiter and maximum prop loiter, you can find the corresponding equations. Now these last two equations, they are for maneuvering flight. So how do you find the wing loading during some kind of maneuvers? So during maneuvers you will be given some kind of turn rate. So this phi dot, this is the turn rate. So from the turn rate you can find out the factor n, which is the excess lift required. And once you know n, then you can use this equation to find the wing loading. So what you can do is you can write, you can square and rearrange it. So n is given by this quantity. So once you know n, you put it into this equation to get the wing loading. Okay, now I am going to discuss a few exercises. So this is the first exercise. So here the answer is both A and D. So for the first option, we know that the stall speed is given by this formula. So you can see that the wing loading and the stall speed, they are directly correlated, which means that if the wing loading is higher, then the stall speed is also going to be higher. Now for the second option, it is low wing width dihedral contributes to longitudinal stability. So wait. So this option is incorrect because so low will wing with dihedral means this kind of a configuration. Now you know that a high wing contributes to lateral stability. Similarly, like a low wing, it adversely affects so the high wing. So a low wing is less laterally stable. So, but when we use put a dihedral in the wings, then it contributes to stability. And if you also remember that the dihedral it prevents the wing tips from hitting the ground during landing. So this option is almost correct, but here it should be lateral. And for the C option, a high wing contributes to lateral longitudinal stability. Uh, No, this is also false, as you saw that the high wing it contributes to lateral stability, and the high wing it does not affect the longitudinal stability. The last option, which is option D, this is correct because as you know that if you have an aircraft like this, aircraft which has a finite wing length, then there is high pressure air below the wing and low pressure air above the wing. So because of the high pressure, you know that a lift force acts on the wing. But at the wing tips, this high pressure air it circulates back up, like it goes above the wing tips and it forms vortices like this. And these vortices it contributes to some these vortices it induces some drag in the aircraft, which is called induced drag. So to prevent this, we install winglets. So it could be something like this, okay, which is sloped up, or you can have a sharp edge like this. So all these constructions of wing at the tips of the wing, you can have a flat plate also. So these constructions at the tip of the wing, they prevent the high pressure air from flowing back up to the top. Okay, so they prevent the flow of air from below the wing to above the wing, and thereby they reduce the induced drag. So the D option is correct. Therefore, the answer is both A and D. This is the second question. So in this case, the if for quad rotor the thrust to weight ratio is more than 1, and for fixed wing aircraft the thrust to weight is much less than 1. So this is the correct answer. Now for to solve this question, we have to find out that how quad rotor and fixed wing they fly. So you know that quad rotor, the propellers produce the four propellers. They produce an upward force, and therefore a total thrust it acts on the quad rotor upwards, and a weight acts on it downwards. And if the thrust is greater than the weight, then the quad rotor moves up. So you can see from this equation only that the thrust should be more than the weight. So the thrust T by W is more than 1. It must be more than 1 to fly up. But when a quad rotor is in equilibrium, let us say that it is hovering. So in this case, the quad rotor is hovering and it is not accelerating up or down, or it is not moving left or right. Then the thrust is equal to the weight. So here in this case, the weight is supported by the thrust. In case of fixed wing aircraft, the weight is supported by the lift. So in case of quad rotor, the thrust loading it is 1, or it might be a little bit more than 1. But when you consider the fixed wing aircraft, the weight is supported by the lift. So the weight is not supported by the thrust in like in the quadrotor case. Weight is supported by the lift, and the thrust is required to cancel the drag. So in this case, the lift is equal to the weight and thrust is equal to drag. So then you can divide the thrust by the weight and it will be 1 by L by D. So we know that L by D is on the order of 10. So it may be 10, 12, 15, and therefore the thrust loading is zero point 0.1, or it could be even below 0.1. So one more thing is that this is the condition during cruise. During climb or during takeoff, more thrust may be required. So you can see that this is much less than 1. So the first option is correct. This is the third question. So in this question, first, like we have to let us convert the speed from 100 kmph to meters per second. We have to divide by 5 by 18. Then let us find out the available power. So the available power is propeller efficiency into the shaft power. So let us first do it for the motor glider. Acha, wait. So we cannot find the available power because the power is not given, but we can find out the power. We can find out P by W. Okay. So you know that. So the approach is this. The approach is that the rate of climb, it is V sine gamma, which is the available power minus the required power by the weight. Now you can expand the required power as T into V. And then you divide by the weight, you get. Okay. So and now further you can use you can calculate T by W during climb. So we discussed that how can we calculate T by W during climb. Okay, so this was the equation. So let me do it for the motor glider. Acha, wait, the climb angle is not given. Okay, so if the so one thing is written that use small angle approximation. So if the angle is small, then sine gamma is going to be small. So we can write that T by W is approximately equal to 1 by L by D, which is hmm. And now the PA by W we can calculate it as. Therefore, the rate of climb, it is equal to So this is coming as 4.76. Hmm. Now, now let us do the second one. Now see, for the second one, the PS by W is 12, and we can find the thrust to weight ratio as 1 by. Comes out to 6.822. So, so this option is the closest. I think there is some problem over here. If maybe there is a calculation mistake, or maybe there is a mistake over here. Okay, now this is the fourth question. So in this case, the answer is increases. So with the increase in wing loading, the corner velocity of the aircraft will increase. Now you can answer this with intuition also, that if the wing loading is increased, then the forces acting on the wing will also increase. Okay, so if you have an aircraft like this, so if the wing loading is high, it means that the forces acting on the aircraft wing are also higher, because a shorter wing is being used to support a larger weight. So when the wing loading is higher, uh, the forces acting on the aircraft are higher, so the corner velocity of the aircraft will increase, because when an aircraft it performs a cornering turn, the uh, forces acting on the aircraft are higher. So you know that during cruise the lift is equal to the weight, but during any maneuver the lift is equal to n times the weight. Okay, so lift is equal to n times the weight. So the wing loading is going to be n times of the cruise wing loading. So if the wait, wing loading at maneuver. So and now when is the n going to be higher? N is higher when the cornering velocity is higher. So when the cornering velocity is higher, the n is higher, which contributes to a higher wing loading. So the opposite is also true. Actually, it should be the opposite, like the higher velocity causes the higher wing loading. The higher wing loading does not cause the higher velocity. But anyway, these two are correlated. So with increase in wing loading, the corner velocity is going to be higher. This is the fifth question. So in this case, the correct answer is A. So the question asks that which of the following options is not correct. So we'll examine all the options. So let us, if you start from the last option, aerodynamic center, the pitching moment coefficients remains constant irrespective of angle of attack. So you know that this is true. If this is the aerofoil and this is the aerodynamic center, then the pitching moment coefficient, which is Cm, it is constant irrespective of the angle of attack. So this is true. The third option, so the aircraft with higher wing loading has a higher stall speed. So you know from the equation that V stall is So the V stall and the wing loading, they are directly correlated. So therefore, aircraft with higher loading will have a higher stall speed. So this is also true. Now the second option, at equilibrium, net moment above CG is zero. So this is of course true. So during equilibrium condition is defined as condition when summation of all the forces are zero and the summation of all the moments are also zero. So this option is also correct. And now the first option, the velocity at minimum power and velocity at minimum thrust are same. So this is not true. You know that for minimum thrust we have to fly it at for minimum thrust we have to fly at CL by CD maximum. But for minimum power we have to fly at CL 3 by 2 by CD maximum. So both these conditions, they yield a different CL, and the different CL, it requires a different velocity. So the velocity at the minimum power and minimum thrust, so they are not same. So that is it for today. So thank you for joining this session.